It is easy to treat a database as a magic box. You put data in, and later you ask for it back. But underneath the software abstractions, every piece of data you save eventually hits a physical medium. The constraints of this hardware are dictated by how it moves. Reading or writing data sequentially, in a continuous straight line, happens at hundreds of megabytes per second. But jumping around the disk to write in random locations incurs severe mechanical delays. To understand why different databases are built the way they are, we are going to build one from scratch, starting with the absolute minimum. You will see that a database engine is merely a specific set of data structures designed to outsmart the physical limitations of storage hardware. The simplest possible database is a 2-line shell script. When you give it a key and a value, it simply appends that text to the end of a file. This design has remarkably good write performance, matching the hardware's preference for sequential disk writes. But a bottleneck emerges when reading data. To retrieve a specific key, the system must check every single entry from top to bottom. At 1 billion records, this scan is impossible. We need an index to speed up queries. We solve this by adding a hash map in memory, storing the direct byte offset where each key lives on disk. Lookups are now instantaneous. But every time we append a new row, we incur a slight penalty, because the system must update both the physical disk and the in-memory map. This demonstrates why indexing is never free. You are permanently trading away write speed and storage capacity to buy back read performance. Even with instant reads, our simple log has a physical limit. By strictly appending every update, old values are never deleted, and the file will eventually consume the entire hard drive. We solve this by breaking the log into segments. When a file fills up, we close it and start a new one. A background compaction process then merges these frozen files, keeping only the newest value for each key and discarding the rest. Compaction fixes our disk capacity, but we still face a memory limit. Because our hash index stores every single key, it must fit entirely in RAM. At 1 billion unique keys, the system runs out of memory. To bypass the limits of physical memory, we have to abandon hash maps and change how the data is physically organized on the disk. The structural solution is sorting. We require that all keys within every disk segment are arranged in order, creating a sorted string table. Because the file is ordered, memory no longer needs an entry for every key. We only need a sparse index, storing perhaps 1 out of every 1,000 keys to act as a guide. This saves massive amounts of RAM, but introduces a mechanical challenge. How do you maintain a sorted file on disk when user writes arrive in completely random order? Incoming writes split into 2 paths. For crash safety, data drops into a sequential disk log. Simultaneously, data enters an in-memory tree, a mem table, that sorts keys as they arrive. When full, it flushes to disk as a pre-sorted segment. This architecture is the log-structured merge tree, or LSM tree. It is the engine behind massive distributed systems like Cassandra and RocksDB. LSM trees are effective for write-heavy workloads because they absorb chaotic random inputs in memory, allowing the hardware to handle the physical data as sequential writes. But the LSM tree pays a price on the read path. To find a single key, a query might have to check the mem table and several older segments before finding the correct value. This latency variability is why relational databases like PostgreSQL and MySQL utilize a different architecture, the B tree. A B tree organizes data into fixed-sized blocks called pages, structured in a branching hierarchy from a root down to the storage leaves. Mechanically, a B tree does not blindly append data. When a value changes, the engine navigates to the precise page and updates it in place on disk. This creates write amplification. Changing a single byte often requires rewriting an entire 4-kilobyte page, consuming I/O bandwidth. The reward for this write penalty is predictable read performance. Because the tree is balanced, locating any key takes the same number of page jumps every single time. Choosing between an LSM tree and a B tree is a zero-sum choice. You either accept read variability or you accept write amplification. Both of these architectures are optimized for looking up individual records, but online analytical processing introduces a different pattern, computing historical aggregates across billions of rows. A typical analytical query doesn't look for one user. It scans a massive table to sum up total sales for a specific product category over 3 years. Row-based databases waste read effort on analytics. Querying total sales forces the system to load every column from disk just to discard them. Data warehouses solve this with column-oriented storage, writing each column into its own file to pull only specific bytes. Isolating columns allows for aggressive compression. Because all the values in a single file share the same data type, contiguous blocks of data pack together cleanly. CPUs process these tightly packed columns using vectorized execution, churning through arrays in lightning-fast batches, rather than evaluating them row by row. Analytical databases can process billions of records in seconds because their physical layout ensures they have to read vastly less data. Ultimately, these underlying mechanical details illustrate the high-level trade-offs required in system design. When you have to absorb a high volume of writes, you employ LSM trees to funnel chaotic random data into sequential append-only logs. When an application requires predictable read latency for users, you rely on B trees, accepting the I/O cost of write amplification. And when the goal is computing massive aggregations, you abandon row-based storage entirely in favor of compressed column stores to eliminate wasted I/O. Every database is defined by these physical trade-offs. The next time you evaluate a system, ignore the marketing materials and the query language. Ask only how it physically writes data